Good day everyone, I am Carmela Luis L. Evangelista from Batangas State University, the National Engineering University of the Philippines. First of all, I am very glad to be a part of this 8th IEEE International Conference on Automatic Control and Intelligent Systems. And today, I will present our paper entitled Long Short-Term Memory-Based Static and Dynamic Filipino Sign Language Recognition. For the introduction, sign language uses an array of gestures made using hands, fingers, arms, head, and some also requires facial expressions. Sign language allows you to communicate with speech and hearing impaired individuals. In the Philippines, Filipino Sign Language or FSLs was recognized as the official sign language of the country. FSL is a distinctive form of sign language with its own set of pose, gestures, and grammar, which can cause a challenge in terms of identifying it. Sign language recognition is an emerging field of research that aims to develop technology to interpret and translate sign language into text or speech. It involves using algorithms of computer vision and machine learning to analyze and recognize the gestures, movements, and expressions used in sign languages. In the Philippines, individuals who are speech impaired or deaf use Filipino Sign Language as a means of communication. Despite being recognized as the official sign language of the Philippines in 2018, FSL remains a relatively understudied sign language of the general public, and many people are still not familiar on how to use this sign language. Recognizing FSL is a challenging task due to its complexity, and a lot of Filipino individuals did not know how to use FSL in a communication with speech and hearing impaired individuals. Earlier researchers have identified 3 categories of sign language recognition methods. These are the glove-based, vision-based, and hybrid. However, the existing studies that presented video-based approaches for Filipino Sign Language recognition are only limited to identifying static sign language such as letters and numbers, and only include limited phrases or words for dynamic FSL recognition. For the objectives, it is seen that the existing studies are only limited to recognizing static FSL and only include limited phrases or words for dynamic FSL recognition. Since the existing studies for dynamic FSL are only capable of recognizing limited words and phrases, this could limit the communication. Thus, adding more phrases and words for dynamic FSL recognition is significant. Also, obtaining a high accuracy rate for Filipino Sign Language recognition is essential since this was used for communication purposes. In this study, the main objective is to develop a Filipino Sign Language recognition system that recognizes both static FSL and dynamic FSL. To be specific, the objective of the study is first to use media pipe holistic pipeline to recognize input body position key points and input hand key points of both static and dynamic Filipino Sign Language from a live video feed. Second is to train a model, specifically the LSTM, that could recognize 24 static FSL, which includes alphabets, and 17 dynamic FSL, which includes common Filipino words, phrases, and greetings. And third, to evaluate the accuracy of the model and visualize it through confusion matrix. For the methodology, the steps involved in this process are the data gathering, data splitting, with 80% for training and 20% for testing, data pre-processing, model training, model evaluation, and model inferencing. For the data gathering, the dataset that was used in this study was manually gathered and provided by the researchers. The dataset used has 24 static Filipino sign languages that includes the alphabet, and moreover, the researchers also included dynamic sign languages that includes common Filipino words, greetings, and phrases. Each class of sign language, both static and dynamic, has 270 sequences, each with 15 frames. totaling to 11,070 sequences. Figure 2 presents the sample images of Filipino Sign Language alphabets, while Figure 3 presents the sample images of Filipino Sign Language common words, phrases, and greetings. In this study, the proponents only utilized 24 post landmarks because the features needed for the recognition are only focused on the upper part of the human body. Meanwhile, the 21 available hand key points from the MediaPipe hands pipeline is shown in Figure 5. This study uses all of its 21 hand key points. It employs machine learning to detect and locate 21 points of reference on hand in a single image frame. For the data splitting, the 11,070 sequences of both static FSL and dynamic FSL are split to be used in training and testing. 80% of the sequences, which is equivalent to 8,856 sequences, will be used for the model training, and the remaining 20%, which is equivalent to 2,214 sequences, will be used for the testing of the model. For the data pre-processing, TensorFlow layer normalization is used to normalize the data by scaling it to a common range or distribution, which makes it more comparable and easier to analyze by the neural network. In this study, during the model training, the LSTM network learns to tune the weights and biases of the gates and memory cells through backpropagation over time. This enables the network to learn long-term dependencies in sequential data and make accurate predictions for static and dynamic Filipino Sign Language. Moreover, in this study, the model training is set to stop at the 227th epoch. Models that have lower loss than the previous lowest will be saved. The model training is done through JupyterLab, and furthermore, Figure 6 presents the TensorBoard generated model architecture. For the model evaluation, after the model training, the generated models are evaluated using the accuracy score formula and visualize it through a confusion matrix for the basis of the evaluation through their accuracy score. And for the model inference, after the evaluation of the models, the model with the highest accuracy score will be used as the final model. This will go through inferencing to determine if the model correctly predicts each static dynamic Filipino Sign Language. For the modeling results, during the training process, the model is fed with training data and adjusts its internal parameters to minimize the loss function, starting at around the 113th epoch and above. The model was able to reach an accuracy close to 100%, and the fluctuations on the other hand are normal due to the factors such as overfitting, noisy data, or insufficient training. The sudden rise and fall of values at the end of the categorical cross-entropy loss graph occurs when the predicted probability of the correct label is very close to 1.0, but not quite equal to it. At this point, the model is very confident that the correct label is the most likely one, but there may still be some small errors in the prediction. As a result, even small deviations from the actual probability of the correct label can lead to large changes in the value of the categorical cross-entropy loss. For the model evaluation results, we can observe that the first few models performed poorly, with low accuracy rates that started from 9%, but as the training continued, the accuracy gradually increased. This indicates that the models were able to learn and improve during the training process. The best model achieved the highest accuracy of 99.72%, indicating that it was the most successful model among all the iterations developed during the training process. Figure 10 presents the remaining 20% of the dataset evaluated through accuracy score and visualize it through confusion matrix. Table 1 presents the percentage of correct predictions for static Filipino Sign Language, while Table 2 presents the percentage of correct predictions for dynamic Filipino Sign Language. Figure 11 presents the 6 samples from the 1917 frame video of static and dynamic Filipino sign languages used to show the inference of the model. The video contains 1917 frames and all of the sign language included in the dataset is performed one by one. There are instances where the model wrongly predicted the sign language, but mostly it is correct. One factor that may contribute to this is the transitioning from one sign language to another, since the dataset only contains segments of videos containing the sign languages. For the average frame rate computation, a total of 1917 frames were used during the inferencing. The frame rate per frame was used to calculate the average frame rate, and it resulted with an average frame rate of 8 frames per second during the inferencing. For the conclusion, the proponents of this study trained a long short-term memory recurrent neural network model using the 24 post key points from MediaPipe holistic pipeline and 21 hand key points from MediaPipe hands pipeline. The proponents utilized a dataset consisting of 24 static Filipino sign languages composed of alphabets and 17 dynamic Filipino sign languages composed of common Filipino words, phrases, and greetings, each with 270 sequences, with 15 frames amounting to a total of 11,070 sequences. This dataset was utilized for the training of the LSTM model. The researchers were able to produce high-accuracy models. The use of LSTM and MediaPipe helped the proponents in creating the model and achieved a 99.72% model accuracy score in recognizing both static and dynamic Filipino sign languages, in which is also visualized through a confusion matrix. For the model testing, it was seen that all of the static and dynamic Filipino sign language, alphabets, basic phrases, greetings, and words are detected by the model with minimal error, and due to the provided high number of data, it improved the accuracy of the model. It was also concluded that the LSTM model achieved an average frame rate of 8 frames per second during inferencing. This high level of model accuracy suggests that the model can be effectively applied in real-world scenarios and applications, specifically for communication. Overall, the objectives of this study were achieved, and the findings of this study demonstrated the potential of utilizing machine learning techniques for Filipino sign language recognition, which could have significant implications for individuals with hearing and speech disabilities in the Philippines. For the recommendation, after achieving a high model accuracy rate, the model still has a lot of potential to be improved. More dynamic Filipino sign language can be added so that it can be more effective and usable for the wide range of users. The future researchers can also add more variations to some sign language, since there are some words that have different ways of being signed depending on the people you are conversing with. Lastly, this can be incorporated in a wearable device for better engagement. These are the list of references that we used in our study. And lastly, the authors of this study are Carmela Luis L. Evangelista, Chris Jericho R. Heli, Mark Marion V. Castillo, and Engineer Carol Biclin G. Macabagdal. Again, thank you so much everyone and have a great day.